Parts of a wave. I hope you can draw a wave. Speed of light. Just remember it's speed, not velocity of light. So there is no direction. That's always a fun one. At what point when the sun explodes, how long do we find out about it? Okay, so this thing phase that sometimes gets people into a bit of a pickle. We are talking about whereabouts the oscillation starts from. So the amplitude could all be the same, but we talk about radians being pi being 180 degrees, the 2 pi being one whole wavelength. And I think I've covered this once before, but indulge me. We often talk about the wavelength on a cable, power cable that is, having multiple phases. Now all of these are at the same amplitude and the same frequency, but they are all on different phases. In fact, we have phase 1, phase 2 and phase 3. Three-phase power, so the name comes from. So none of these will actually be added together. We'll talk about constructive and destructive interactions in a second. Okay, so constructive. Now, if I draw our wave here, and I'll start with a nice red wave. Okay, and I'll stop, and the red wave is traveling in that direction, and I will do the same wave down here. Okay, now if I switch to, come on, let me switch. I have not cracked this bit yet. Let's go for blue. Okay, so with constructive, this time our wave is going to come in from down here, and it's going to be at the same frequency. Now it doesn't have to necessarily be at the same frequency for the whole time. It might just be that frequency for a given wavelength at that point. Now, if this was a wave, is a good example. If I was okay. So if I had the amplitude of both the red wave and the blue wave, they actually end up stacking on top of each other. Conversely, in the negative. So you actually end up with these massive, big amplitude spikes. So, an example of that might be an offshore drilling rig where you've got waves meeting from different currents, and if they happen to get into the same phase and meet at the same point, they actually increase the amplitude. This would be a massive wave that could do quite a bit of damage. Now, that's constructive or superposition. Constructive superposition. Destructive superposition is probably the more interesting one for those of you who have noise cancelling headphones. This time around, I know I should swap back to blue, but I can't bother to. So this time we've got our wave going the opposite way. Now, the way this would be generated is, what would happen is you'd have a little microphone on the outside of your headphones that would hear that frequency. And what they do is they then create another frequency that's 180 degrees out of phase, and play it to you at the same time. So inside your ear, what you're actually hearing, apart from your music hopefully, let's go to blue this time. So you're hearing your music mix. This is just the outside noises, and this is why they're called noise cancelling. These two, if at this point here, would be 0. So inside your headphones, excluding obviously the music you try and listen to, the outside noise is cancelled because of they match up all the noises outside and play the corresponding note or frequency that it's 180 degrees out of phase, and hence you end up with this lovely 0, ideally in a perfect world, noise cancelling headphones, and that's why they tend to be more expensive. Okay, so this is covered a lot more in 5.5, where we talk about tension in a string, and we'll look at fundamental frequency. So don't spend too much time writing this one down. Go on to 5.5 and crack on from there. But that's the end of the narration for this slide.